Welcome back to Basic Electronics. In the last lecture, we were looking at a simple BJT circuit which can be used as an amplifier. The gain of that amplifier is determined by the slope of the VO versus VI curve. We will now see how this gain is affected by the various parameters, that is, the resistances and the transistor beta. After that, we will look at the effect of DC bias on the collector current waveform when a sinusoidal base to emitter voltage is applied. We will look at a simple scheme to bias the transistor at a specific value of collector current. Okay, let us start. Let's look at the same circuit in some more detail. Here are the choices for RC, 0.5K or 1K or 2K. For RB, 1K or 5K or 10K. And beta can be 50 or 100 or 200. And if the transistor is in the linear region, VO is then given by VCC minus IC RC, and IC is beta times IB in the linear region. So we get RC times beta times IB here. And IB is approximately VI minus 0.7 because VBE is approximately 0.7 divided by RB. And this is a straight line in the VI-VO plane because VI comes with a constant coefficient here. What are the limits of this equation, the validity of this equation? First, when VI is less than 0.7, the transistor is in the cutoff mode, so this equation is not valid. And when VO becomes VCE sat or 0.2 volts, then this equation ceases to be valid. So those are the limits. Between those two limits, the transistor is in the linear region and we can use this equation. Let us now compute the VO versus VI and other quantities, and these are the graphs. So that is VO versus VI. It looks familiar. We have seen that in the last slide. These other quantities we did not see explicitly, so let's look at these now. What about IC? IC versus V in. It is 0 in the beginning because the transistor is in the cutoff region when VI is less than 0.7 volts. Then the transistor enters the linear region, all of this, and that is described approximately by this equation. And so IC keeps increasing. At some point, VCC minus ICRC becomes equal to 0.2, and that is the point where the transistor enters saturation. And that is here. And after that, this VCE really does not change too much. It remains between 0 and 0.2 volts, and therefore IC remains approximately constant. What is that constant in this case? It is 5 volts minus, let's say, 0.2 volts, 4.8 volts divided by RC. RC is 1K, so about 4.8 milliamps. And that is what this is. This is 2 milliamps, 4 milliamps, so that's nearly 5 milliamps or 4.8 milliamps. Let's look at VBE versus V in now. In the beginning, the transistor is off. We are now in this region or this region here where the transistor is in cutoff. And VI and VB are the same, so therefore VBE is equal to VI. And that's just a straight line with a slope of 1 passing through the origin. So that is what that is. And at this point, the transistor enters the linear region. The base emitter junction is sufficiently forward biased. So this voltage drop is going to be something like 0.6 to 0.75 volts once the transistor starts conducting. So that is what we see over here. And eventually, when the transistor enters the saturation region, the base emitter junction remains under forward bias, and therefore VBE is still 0.7 or thereabouts. What is this voltage here? This is 1 volt, 0.2, 0.4, 0.6, 0.8, so that's something like 0.7 volts. What about VBC? VBC is the forward bias on the base collector junction. In the beginning, the transistor is in the cutoff region. VB is equal to VI because this voltage drop is 0, and VC is pulled up to VCC because there is no IC RC drop over here. So VBC is then VI minus VCC. So that is again a straight line with a slope of 1, that part there. At this point, which is the same as this point here or this point here, the transistor turns on and enters the linear region. And now for VO we have this equation. VB will not change too much beyond this point. It will stay at about 0.7 volts, and therefore VBC will start rising, and that is because this voltage is falling, this voltage is constant, so therefore VBC will start rising, and that is what is seen over here. Finally, when the transistor enters saturation, at that point the base collector junction is sufficiently forward biased, and that is happening at about this point here. So this is 1 volt, so that is about 0.6 volts, and subsequently with further increase in VI, the base collector junction remains forward biased throughout here. Let us start the animation now. Pause. We are now in the cutoff region. The collector current is 0. If the collector current is 0, VO gets pulled up to VCC. That is what we see here. The base collector junction is under reverse bias. VBC is between -5 and -4, and VBE is positive, but it is not sufficiently large to make the base emitter diode forward biased, and therefore the collector current is still very small. Let's continue. And now we have entered the linear region. In the linear region, the collector current has started rising, and because of that this voltage drop has increased, and therefore VO has become smaller. VO, which is VCC minus IC RC, has become smaller, and that is what we see over here. VBC is still less than 0.7. In fact, it's negative at this point, and the base collector junction is therefore still under reverse bias. VBE is now something like 0.6 to 0.7 volts, and that is large enough to give rise to substantial IC, and that is what we observe here. Let us continue. At this point we enter the saturation region. VO has become equal to VCE sat because the transistor has entered saturation. VCE sat is like 0.2 volts or smaller, and that is what we see here. IC has reached its maximum value, and that is 5 volts minus about 0.2 volts divided by RC, which is 1K. So that is about 4.8 milliamps. The base collector junction is now under forward bias because VBC has become something like 0.6 volts. The base emitter junction continues to be in forward bias, and beyond this point things are not really going to change except for the input voltage. What happens to the extra voltage? This is increasing, this is constant, so the extra voltage gets dropped across RB. So things really don't change after this point. Let us now look at the effect of RC, RB and beta on these curves. For example, if we change RC from 1 to 0.5, what do we expect? Will this part change? That will not change, because that depends only on the on voltage of the base emitter diode. How about this part? Even that will not change, because that is simply VCE sat for the transistor. So what will change is this part here, the one that corresponds to the linear region, and that is because we have RC here in the equation for that region. So RC controls the slope of the VO versus VI characteristics. It's beta times RC by RB. So if we make RC smaller, the slope will become smaller. Note that it is still negative. So this variation will become less steep. So let us see if that happens. Like that. And correspondingly, these other curves also will change. Let us now look at the effect of RB. For example, if we change RB from 5K to 10K, what would happen? Let's look at this equation again. The slope depends on RB, beta RC by RB with a minus sign. And if RB is doubled from 5K to 10K, the slope will then become halved. So once again, this region will become less steep than it is now, and let's check that out. It does. And correspondingly, of course, the other curves will also change. What about beta? Suppose we change beta from 50 to 100. Let's look at this equation once again. So the slope goes directly as beta. So if beta has increased, the slope will increase. So therefore, this region will now become more steep. And let's check that out. It has become more steep, and there is a corresponding change in all of these other plots as well. This circuit, by the way, is also called a BJT inverter. This term inverter comes from digital logic, and what it means is if the input voltage is low, the output voltage is high, and if the input voltage is high, then the output voltage is low. And that is exactly what this circuit is doing, and that's why it's also a BJT inverter. It's also an amplifier, because in this region there is a small change in VI, then there is a large change in VO, and that's why it's an amplifier as well. We will look at that in more detail soon. For this circuit to function as an amplifier, what we need is a large enough gain, which is given by dVO dVi, that is the slope of this VO versus VI curve. And it's clear that the slope is maximum somewhere here in magnitude. Since VO is nearly constant for VI less than 0.7 volts, and that happens because of cutoff, and also VO is nearly constant for VI greater than 1.3 volts, and this 1.3 volts of course is specific to this example with some given values of RC, RB and VCC. In these two regions, the circuit will not work as an amplifier, because the slope here as well as the slope here is nearly zero. so it is not really useful for amplification. Further, to get a large swing in VO without distortion, the DC bias of VI should be at the center of the amplifying region. So this is the amplifying region where we have a good large enough slope dVO dVi, and we now are saying that we should not only operate in this region, but we should operate somewhere at the center of this region. And this point will become more clear in the next slide. Here are the Vi and Vo graphs which explain how amplification happens in this circuit, the same circuit as the one in the last slide. What is the input voltage waveform here? There is a DC component of about 1 volt. So we are applying an input voltage which is centered around this 1 volt. The input voltage is going to go like that with time. The amplitude of the input voltage is from 1 to 1.05, that is 50 millivolts, and the peak to peak value of the input voltage is 100 millivolts or 0.1 volt. What about the output voltage? Here is the output voltage. The first thing we notice about the output voltage is that it is out of phase with Vi. There is a phase difference of 180 degrees between Vi and Vo, and that is easy to understand. As Vi increases, Vo decreases, and that is why dVo dt dVi is negative, and that is reflecting basically in this phase relationship between Vo and Vi. What about the amplitude of Vo? Let's look at the peak to peak voltage here. It's roughly 2.4 to 3.4, so it's about 1 volt, slightly less, and so therefore we see that there is a gain of 1 volt divided by 0.1 volt, or about 10, a little less than 10, and that is what we mean by amplification. Let us now consider another DC or bias value for the input voltage, and that is given by this line A here. And what we are going to do is apply an input voltage which varies about this point, and then see what the output voltage looks like. So that is the input voltage now. This DC bias, which is 0.75 volts, corresponds to this line A here, that is 0.75 volts there. Apart from that, the input voltage in this case is the same as the input voltage in the earlier case, the B case. The amplitude is still the same, so it's 0.1 volt or 100 millivolts peak to peak. All that has changed is the DC bias here for the input voltage, and as a result the output voltage looks like this. It is distorted, and it's easy to see why the distortion is happening. Let's look at this line A. If we go to the right of line A, that is increasing Vi, we see that the picture is different than if we go to the left of A. In this case, in the earlier case, we had the same gain in both directions, and now the picture is completely different. If we go to the right, there is some gain, and if we go to the left, the gain is much smaller. The derivative here is much smaller, and that is reflecting basically in this distortion. This situation is definitely not desirable, and therefore we will not operate the amplifier at this DC bias. Let us consider another bias point, the one given by this line C here, and we are going to apply an input voltage which goes around that bias point like that, and let's see the input and output waveforms now. That is the input voltage centered around 1.3 volts, which is this value here, and the amplitude is still the same. It is 1.25 to 1.35 peak to peak, so 0.1 volts peak to peak or 100 millivolts peak to peak. And as a result, the output voltage is again highly distorted, and it's easy to see where that is coming from. The left side of C is now quite different than the right side of C. Here we have some reasonable gain, here the gain is very small, and that is where the distortion is coming from. So the point to take home is that bias point is extremely important in BJT amplifiers. In fact, that is true about amplifiers based on any devices, whether it's a MOSFET or a JFET or a BJT. The circuit file for this example is available to you. You can check out these results. You can also change parameter values and see what happens. So here are the key challenges in realizing this BJT amplifier in practice. One, adjusting the input DC bias to ensure that the BJT remains in the linear active region with a certain bias value of VBE or IC, and we saw that that corresponds to a bias value which is in approximately the center of this region here. That is one challenge. So we have to apply an AC voltage which is riding on a DC value which is approximately at the center of this region. How do we ensure that? That's one challenge. Second, mixing the input DC bias with the signal voltage. So we have two components to the input voltage. One is this DC bias, which we want to be at the center of this region, and on top of that we want to have the input voltage. How do you mix these two input components, DC and AC, or DC and signal in general? The first issue, adjusting the DC bias of the input voltage, is addressed by using a suitable biasing scheme, and we will see some of the biasing schemes. And the second issue of mixing the input DC component and the signal is achieved by using coupling capacitors, and we'll also take a look at that. Let us consider this simple biasing scheme shown in this circuit. Biasing means selection of component values RB and RC here for a certain DC value of IC. And as we have seen earlier, that is equivalent to setting up a certain DC value of VBE, the base emitter voltage. For example, a DC value of 2 milliamps for IC may correspond to a VBE value of 0.672, for example. And let us remember that no signal is applied at this stage, so the signal is 0, and the solution of this circuit will only give us the DC or bias values, and we will worry about how the signal is going to be mixed later. Now equivalently, we may bias an amplifier for a certain DC value of VCE, this voltage VCE, and why can we do that? Because IC and VCE are related. For example, in this circuit, VCE plus IC/RC is equal to VCC, and so therefore there is a relationship between VCE and IC. So sometimes instead of insisting on a certain value of IC, we might say that VCE should be a certain voltage. As an example, let RC be 1K and let the transistor have a beta of 100. With these conditions, let us calculate RB, the resistance here, for IC equal to 3.3 milliamps, and we will assume the BJT to be operating in the active mode. And of course we need to come back and check whether that condition is indeed satisfied. Simple calculation. If we know IB, if we know IC, we also know IB. IC divided by beta, 3.3 milliamps by 100, 33 microamps. And what is IB? Is this current, and that is 15 volts minus VBE divided by RB. So that is 15 minus 0.7 divided by RB. So we have an equation now for RB. Using this number we can calculate RB. So RB turns out to be 430 kilo ohms. So if we have RB equal to 430 kilo ohms and with RC equal to 1K and the transistor beta equal to 100, we can expect the collector current to be 3.3 milliamps. Is the transistor indeed operating in the active mode with this with these component values? That's easy to check. Let us calculate VC. VCC is 15 volts. IC/RC is 3.3 times 1, so 3.3 volts. So VC is 15 minus 3.3, around 12 volts. VB is about 0.7. So this is a P region. P region is at 0.7 volts. N region is at 12 volts or thereabouts. Therefore definitely this BC, base collector junction, is reverse biased, and the transistor is indeed operating in the linear region. Let us summarize. With RB equal to 430K, which we computed in the last slide, we expect IC to be 3.3 milliamps if the transistor beta is 100. Now it turns out that this if here is a big if. Let us see why. In practice, there is a substantial variation in the beta value, even for the same transistor type, such as BC107. The manufacturer may specify the nominal value of beta as 100, but the actual value could be 150, for example. There is a wide variation possible, and that has to do with the manufacturing process for the BJT. So with this very wide variation in beta, can we still trust our numbers? Let us check. With beta equal to 150, the actual IC is beta times IB, which is VCC minus VBE by RB, and that is 150 times 15 minus 0.7 by 430K. We have already picked this RB, assuming that our beta is 100, but the actual beta of this transistor happens to be 150, and the current then would be that expression, or 5 milliamps. Now this current is significantly different, obviously, than the intended value, which is 3.3 milliamps. So we designed the circuit for a collector current of 3.3 milliamp, but when we hook it up, we might find that the collector current is 5 milliamp, because the transistor beta is not what we expected it to be. So this is a problem, very relevant problem in practice, and certainly we need a biasing scheme which is not so sensitive to the beta value. To summarize, we have seen that the DC bias is very important for a BJT amplifier to work properly. We looked at a simple biasing scheme and observed its limitations. In the next class, we will look at an improved biasing scheme. See you in the next class.